to our third installment of the winter school. We hope you're all enjoying the talks so far. Just before I hand over to Bernhard, don't forget that we have our socialization sessions in Gathertown after the talks, which is a good opportunity to come and interact with other participants and the speakers as well, if you have questions. Another thing is, just as a reminder, in Bernhard's talk, if you have questions, you can post them in the chat at any time. But what will happen is that about halfway through, Bernhard will take a short break to answer the questions that have appeared there. And also at that point, you can just unmute yourself and ask a question, and then similar at the end of the talk as well. Okay, so it's my pleasure to introduce Bernhard Keller for the last installment of his course on A-infinity structures. And Daniel, don't forget to press record.
Thank you very much. Yes, I forgot to put the slides into the folder. I'm doing it right now. I just have to wait for the export to finish. Well, in the meantime, the plan for today is as follows. I will start with a reminder. I will remind you of the formulas defining A-infinity algebras and the formula defining morphisms of A-infinity algebras. So these formulas are quite complicated with lots of signs. And our first aim today will be to rewrite these formulas in a more compact way and without any signs. And for this, we will use the bar construction. And then the second aim is to construct the derived category of an A-infinity algebra and of a homologically unital A-infinity category. And inside this category, we have this is in general a huge category, but inside we have a nice, essentially small subcategory, the triangulated subcategory generated by the representable functors. And we will, at the end, I will give a construction for an A-infinity category whose H0 is this triangulated subcategory generated by the A-infinity, by the representable functors. And this A-infinity category is the A-infinity category of twisted objects. And now, just a moment. Okay. Let me put the slides into the folder. Just a moment. Okay, so it will take a few minutes. The upload will take a few minutes, but if you wait a few minutes, then you can download the notes.
Bernhard, I think you can put directly the file to the chat.
Yeah, it's a bit too big. Well, anyway, it's already in the folder. Just a moment. Okay, so right now you have to wait a little for the upload to be finished. Okay. Okay, so now let me start the lecture itself. Okay, can you see the screen? Yes? Okay. Yes. So let me quickly give the reminder, which I already gave orally. We start with a field, then an A-infinity algebra is a Z-graded vector space together with n-ary multiplication maps for each n, which are of degree 2 minus n, and which satisfy the A infinity equations, quadratic in the multiplications and with certain signs. We have interpreted these equations for small n. Then we have seen the notion of A infinity morphism. It's given by a family of graded maps homogeneous of degree 1 minus n, which again satisfy certain identities with even stranger signs. And well, as I said, our first aim is to rewrite these definitions in a compact way and without signs using the bar construction. And then the second aim is to construct the derived category. And inside the derived category, the H0 of the category of twisted objects. Okay, so let's start with the bar construction. Well, for a graded vector space V, we define the reduced tensor co-algebra in this way. So it looks like a tensor algebra, yes, but without the k, yes, that's why it's called reduced. Just the sums of the positive, strictly positive tensor powers of V. But we take it as a co-algebra, so instead of taking the concatenation product, we endow it with the deconcatenation co-product. Okay, so well, we take a tensor with n factors and we cut it at these positions. And then, well, in particular, if there's only one factor, then, well, then the second factor would be empty and hence 0. So if we have only one factor, then the deconcatenation by definition vanishes. If we have two factors, well, we split them in the middle. Okay. Now, if we have more factors, yes, suppose we have a tensor U with many factors, and suppose we apply some iteration of the co-multiplication to this multiple tensor, well, if the iteration is high enough, then it's easy to see that this will vanish. And we say that the co-algebra is co-complete. So it's locally co-nilpotent. Okay, so it has this special property. And well, it is endowed with the canonical projection onto V. So we have a projection from this co-algebra, from this co-complete co-algebra to V. And this projection has a universal property. It is in fact universal among all graded linear maps from some co-complete co-algebra to V. Okay, so let me draw the corresponding diagram. Yes, so we have our co-free co-algebra reduced. We have the projection onto V. So this is a map from a co-algebra to V. If we have any more linear map from a co-complete co-algebra C to V, then this linear map uniquely factors by a co-algebra morphism through this co-algebra. Yes. Well, this may look a bit confusing at first, but it is quite natural. It is the exact dual property of the classical universal property of the tensor algebra. Yes. So let's look at the reduced tensor algebra. Again, the same vector space, but now considered as an algebra for the concatenation product. Then instead of having this projection, we have the inclusion, which is a linear map from V to an algebra. And this is universal among all linear maps from V to an algebra. When you have a linear map like this to an algebra, an associative, but usually non-unital algebra, there's a unique extension to an algebra morphism defined on the tensor algebra. And as you can see, these two diagrams are exactly dual to each other. Yes, they are obtained from one another by reversing the arrows. And well, as you will perhaps remember, there's a second universal property for the algebra, this time not for morphisms, but for derivations. Yes, when we have, suppose we have a linear map from V to the tensor algebra, some linear map, then it's easy to check that it extends to a unique derivation. Yes, there's a unique derivation defined on the tensor algebra, which restricts to the linear map and satisfies the graded Leibniz rule. And this property also dualizes to this setting. Yes, let's take a graded linear map defined on the reduced co-free co-algebra. Then it's not hard to see that it uniquely lifts to a co-derivation. Yes, so we have this linear map, and we can lift it to a co-derivation of the algebra in a precisely dual way. And co-derivation means this. Yes, this is exactly dual to the Leibniz rule for a derivation. Yes, here you first do a co-multiplication and then you apply this, which is exactly the opposite of the usual Leibniz rule for algebras. And you can check this universal property as an exercise. And we can make the components of this map explicit, namely, yes, so this linear map will take the V tensor n component of this source to some V tensor u component of this target. And this component from V tensor n to V tensor u, well, it's exactly given by this expression, well, which may look familiar already. Okay, and we will use this in a moment. Okay. And so thanks to this universal property, we get a bijection between co-derivations, graded co-derivations of the tensor co-algebra with graded linear maps from the co-algebra to V. Yes, so whenever we have such a co-derivation, we just have to compose it with the projection onto V that gives us the linear map. And conversely, by the universal property, if we have a linear map, it extends to a co-derivation. Okay, and now we will use this. Let's apply it to a graded space called A. More precisely, to the suspension of this graded space. We shift our graded space by 1 degree to the left. And then we need the canonical isomorphism of degree -1. Yes, we just take an element, a homogeneous element, little a of big A, and take it to the same element, but shift it by 1 degree to the left. So this is an isomorphism of degree -1. And now, using this isomorphism, we can define a bijection between linear maps of degree 2 minus n from A tensor n to A, and linear maps of degree +1 from the nth tensor power of the suspension to the suspension. And so this is just some degree shifting trick, but it is not entirely trivial because there are some signs hidden here. Yes, so how do we define this bijection? Well, in the natural way, yes. So let's say we have this bn on the left-hand side of degree +1. Then we compose it with the nth tensor power of our isomorphism of degree -1. And then we compose it with the inverse of the morphism of degree -1. Okay, so the degrees add up correctly, yes. -n + 1 equals 1 minus n, and 2 minus n + 1 also equals 1 minus n. So this actually makes sense. And because these are isomorphisms, it defines the required bijection. Okay. Now we have chosen this square to be commutative, yes. And this is actually not dictated by the causal sign rule. Yes, the causal sign rule doesn't tell us much in this situation because we're not commuting two elements. Yes, so these pairs of elements are distinct. So the causal sign rule doesn't apply. And in choosing this square to be commutative, we have made some choice, some sign choice. Yes, we could have chosen the square to be anti-commutative. We get a different sign choice, or we could have chosen the square to be commutative depending on n, -1 to the nth commutative. Yes, all these are possibilities. These give different sign choices and they give different sign conventions for A infinity algebras. Okay. Okay, and now the promised rewriting of the A infinity identities for the structure maps of A infinity algebras. Yes, so we assume that we are in this situation. We have a family of maps Bn in bijection corresponding to a family of maps Mn. Then the maps Mn define an A infinity structure, A infinity algebra structure on A, if and only if the corresponding co-derivation B is a differential. And this, you can express this in terms of the components of B, and it reduces to this identity, which looks exactly the same as the defining identity for the MNs, except that there are no signs here. Yes, so all authors agree on the fact that in this identity for the B's, there should be no signs, but then there is a disagreement about how to translate this into an identity for the MN with signs. So the convention I have followed is the convention of Getzler and Jones, but there are other conventions. Okay. Yes, and now some notation. We call reduced bar construction the pair consisting of this co-algebra and the suspension together with the differential associated with the family Mn. And then this also works for morphisms. Yes, so morphisms whose definition I've just recalled. Yes, you can check that using the universal property, you can check that morphisms between A infinity algebras correspond precisely to morphisms of differential graded co-algebras. Yes, where a morphism of differential graded co-algebras is just a map which preserves all the structure, a graded map preserving the compatible with the co-multiplication and compatible with the differential. So here we have the naive definition of morphism. Here we have a non-naive definition. Okay. Now we can use this to define homotopies between morphisms of A infinity algebras. Okay, so let's take two A infinity algebras, A and A prime, and two A infinity morphisms. Let's write capital F and capital G for the corresponding morphisms of DG co-algebras. And we will define a homotopy between F and G using this translation. And in the translation, it becomes quite simple. Yes, so a homotopy capital H from capital F to capital G. Well, it's a graded morphism of degree -1, whose boundary in the morphism complex is simply the difference of F minus G. Yes, and which satisfies this additional property. Well, what does this property mean? Well, thanks to F and G, the bar construction of A prime becomes a differential graded bicomodule over this object. So here we have a bicomodule over this object, the left module structure, the left co-module structure being given by F, and the right co-module structure being given by G. And what this says is that H is a co-derivation from the bar construction of A to this bico-module. Yes. So it has a simple structural interpretation. So this is a homotopy between capital F and capital G. And then this, of course, translates into a family, again, a family of maps of degree -n, which satisfy suitable conditions, yes, compatibility conditions with the multiplications. Sorry, yeah. Okay, which we can translate this equality, and we can translate, we will just get the consequences of this equality. We already use this equality in the translation from H to this family. Okay. And now it's a remarkable fact that homotopy is actually an equivalence relation on this set of morphisms, which is compatible with composition on the right and the left. This is trivial. This is not so obvious. It's not extremely hard either, but it's not clear. And notice that I mean, if you try to do something analogous for algebras, yes, you can imitate this definition for morphisms between algebras, but ordinary algebras, but if you do that, what you get is not an equivalence relation. Yes, it will not be transitive. You can close it up, but a priori it is not, unless the algebras you use are free algebras. Then it also works. And so here they are co-free, and that's why it works. Okay, and then the second point is that a morphism of A-infinity algebras is a quasi-isomorphism. Remember, that means that the first component is a quasi-isomorphism, if and only if it becomes invertible modulo homotopy. So all in this in the world of A-infinity algebras, all quasi-isomorphisms of A-infinity algebras become actually homotopy equivalences, yes, which is quite surprising at first sight. Yes. And now there is an analogous result for homologically unital A-infinity categories, where we replace quasi-equivalences where we replace quasi-isomorphisms by quasi-equivalences. Yes, and I need them to be homologically unital in order for quasi-equivalences to make sense. Yes, remember, a quasi-equivalence is in particular a functor which induces an equivalence of categories in H0. And in order to speak about an equivalence of categories, I need to speak about identity morphisms. Yes, I want to speak about isomorphisms, so I need identity morphisms. And in order to speak identity morphisms in H0, I need this condition of homological unitality. Okay, and well, one can improve on this theorem on the second part by showing that if we localize the category of DG categories with respect to quasi-equivalences, then we get a category which is equivalent to the localization of A-infinity categories with respect to quasi-equivalences, or equivalently to the homotopy category of A-infinity categories. So at the level, this a priori is a statement at the level of ordinary categories, and in this form it is proved in great detail in in a paper by Canonical Ornari and Stellari from 2019. One can enhance it a bit to the level of infinity 1 categories. That's in a recent preprint by O and Hiroli Tanaka. And well, the correct setting would be that of infinity 2 categories, but according to O Tanaka, that is not yet clear. Okay. Yes. Are there any questions so far? Let me have a look at the chat. Yes. I think the sum and the concatenation product should be up to n-1, not n. In the deconcatenation product, let's have a look. I think, well, let's have a look. Yes. Yes, so you see the last component in this left tensor is vi, and so I think I want it to be vn-1. Yes, because the last component, the second tensor factor, should always be non-empty. Yes, so for example, here it goes from 1 to 1. Yeah. So from 1 to n-1. Absolutely, you're right. Yes. N-1. Yes. Thank you. And can we define homotopy more directly? Yes. We can write down what a homotopy is, just in terms of a family of graded maps Hn of degree -n, and such that we have a certain equality involving the fn's, the gn's, and the hns. Yes, so so the h's don't have to be compatible with the differentials, but then the equality don't have to be compatible with the mn's, but then the equality involves the f's, the g's, and the mn's. Yes, so we can give a completely direct and explicit definition. Absolutely. Yes. Yeah. So thanks to this co-derivation condition, we can use the universal properties, and this gives us the translation. And once we have translated, only this yields a condition which involves f, g, the mn's, and the hns. Could you explain again the transition from different commuting squares to different sign conventions? Yes. I mean, yes. So, okay, here we have the identity without signs. So, for example, we have this expression. And now imagine that you compose this expression which has u arguments. So you compose it, say, on the right with S tensor u. Yes. If you do that, and then you rewrite it. When you rewrite it, you will slide certain factors S through the BS, and this will produce signs. Yes, and and also if you, on the other side of the equation, if you commute things, you will get more signs, and depending on which sign convention you have chosen on this square, the final sign will be different. Yes, so yes, yes, so you have to imagine that, yes, so this Mn is obtained, yes, so you have this Bn composed with S tensor n gives us this composition, and when you apply this translation process to expressions of this type, then because S is of degree minus one and Bs is of degree minus one, you get more signs. Okay, if I understand correctly, DG categories up to quasi-equivalence form an infinity 2 category, yes. But I also read that A infinity categories are basically equivalent to DG categories, yes. That is correct, yes. So they also form an infinity 2 category. I guess something is wrong here based on what you said. No, so what Tanaka and O do, well, they only consider the non-full sub-2 category, where for two morphisms you only take the invertible ones. Yes, so they truncate this infinity 2 category to an infinity 1 category, and then they, yes, yeah, I hope. Perhaps because this only hold one K is a field. No, I think the K doesn't matter here. Okay. Are there more questions? Okay. Then let's come to the derived category. Yes, and so here all the proofs can be found in Kenji Lefebvre Hasegawa's PhD thesis from 2003. Let's fix an A infinity algebra A. And now we use the non-reduced bar construction. We just take the reduced one and add a factor k in such a way that we get a co-augmented co-algebra. So explicitly we add a k to the reduced one. Then we add new terms to the co-multiplication, yes. And we extend the differential in the natural way. Okay, and then for each graded vector space, we have a co-free co-module V tensor BA with the natural co-free co-multiplication. And we define an A infinity module to be a graded vector space M endowed with a co-module differential. So we on this, we take this co-module as a grade, we fix this graded co-module, and we just look at the differentials, the possible differentials for this co-module. And the possible differentials, by definition, give us the possible A infinity structures on this graded vector space. And then we write Bm for the co-module with its differential. Okay, and again, we can translate this in terms of, well, either a family Bm, which satisfies the A infinity equations without signs, or into a family Mn, which satisfies the equations with signs. And the equations are actually practically the same as the equations for the A infinity algebra. We simply have to reinterpret the m's which appear in the equations for the A infinity algebras depending on the arguments. Yes. So when we have in the expression, when we have an m which involves the first argument, we have to interpret it as the module multiplication. When we have an m which only involves these arguments, we have to interpret it as the algebra multiplication. Okay, and so these equations then in particular show that the homology of M becomes an ordinary module over the graded algebra given by the homology of A. Okay, so this is the A infinity version of the module. And in particular, the algebra itself becomes a module over itself. If you like, you can call it the free A module of rank 1. Okay, and later we will need to look at homologically unital modules. So if the algebra itself is homologically unital, then we say that the module is homologically unital if its homology is an ordinary unital module of this unital graded algebra. Okay, and then we have a natural notion of morphism, which we can just define as a morphism of differential graded co-modules. And this again translates into a family of maps satisfying suitable compatibility conditions with the MNs or the BNs, as you like. And we say, so among these maps, they're defined for n at least 1. In particular, we have F1, which is going to be a morphism of complexes. And we say that F is a quasi-isomorphism if its first component is a quasi-isomorphism. And then we can even define a morphism complex. Yes, so the nth component of this morphism complex consists of the graded morphisms of degree n, morphisms of graded comodules, but these morphisms don't need to preserve the differential, and the differentials are encoded in the differential of the morphism complex. Yes, as one does over an algebra, it's precisely the precisely analogous construction, and in this way, the category of A infinity modules becomes a DG category. Yes. Yes. I mean, you can view. Well, there's a general notion of A infinity functor category. When you have two A infinity categories, you have an A infinity functor category, and if the target is a DG category, then this A infinity functor category becomes a DG category. And this is an example of this type. Yes, we look at A infinity functors from the A infinity algebra to the differential graded category of differential graded vector spaces. And that's the reason why we get a DG category. And using this morphism complex, we can define homotopy for morphisms between A infinity modules. Okay, and again, we have the analog of the theorem for A infinity algebras. Yes, when we have a morphism is a quasi-isomorphism if and only if it is invertible up to homotopy. And the localization, this homotopy relation is of course compatible with compositions on the left and the right. And if we localize the category of A infinity modules with respect to quasi-isomorphisms, we get a category isomorphic to the quotient of this category by the homotopy relation. Okay, and now we define the derived category. I do this only in the homologically unital case. Namely, we take the category of homologically unital A infinity modules and invert the quasi-isomorphisms, or equivalently, we take this same category and pass to the quotient modulo, the homotopy relation. So in this case, we don't need to invert quasi-isomorphisms artificially. They are already invertible up to homotopy. Okay, now this derived category is, you can show that it is canonically triangulated. That's not hard. In fact, you can check that the co-free DG co-modules form a Frobenius category whose associated stable category is precisely this homotopy category, and so it becomes triangulated. And we can do essentially the same definitions for homologically unital A infinity categories. And well, later the free module will play an important role, and the free module has to be replaced by the collection of representable modules. Okay, now let's look at what happens if we apply this construction to an ordinary associative unital algebra concentrated in degree 0. Yes, then each complex of A modules can be viewed as an A infinity module, but there are usually many more A infinity modules. You can have non-trivial higher structure on a complex of A modules. So, so this category, this derived category, whose objects are the A infinity modules over A, has usually many more objects than this category. But nevertheless, the inclusion yields an equivalence, which is somehow reassuring. So if we can look at A as an ordinary algebra or as an A infinity algebra, and the derived category does not change if we change our perspective. So in particular, this means that when we have an A infinity module, we can always, up to homotopy equivalence, we can always strictify it. We can always get rid of the higher operations and only conserve the differential. Yes, if we accept to replace our object by a homotopy equivalent object. Secondly, this derived category is preserved under A infinity quasi-isomorphism. Yes, so when you have an A infinity quasi-isomorphism, it's easy to define an A infinity restriction functor. Yes, this equivalence is an equivalence of triangulated categories. Yes. Yes, so you can define this A infinity restriction functor, and it is an equivalence. Okay, as in the case of DG algebras and DG categories. And so, well, this derived category, well, it's an unbounded derived category. It has arbitrary coproducts given by coproducts of, let's say, comodules, or equivalently of complexes, yes. And so this category, triangulated category with coproducts, is a compactly generated category. It's generated by the free A module of rank 1, as in the case of a DG algebra or an ordinary algebra. I don't know. If you don't know what compactly generated means, then please type a question mark into the chat and I will define it. So let me wait for the question marks. Okay, there's one question mark. Okay, so yes. So if we have an object C is compact, by definition, if hom C commutes with arbitrary coproducts, yes, so this, since our category has arbitrary coproducts, it makes sense to state this definition. Okay, and then it turns out that the free object, well, the free module, if you look at hom from the free module, you get homology in degree 0. And homology in degree 0 is a functor which commutes with arbitrary co-products. And so this object is compact inside this triangulated category with co-products. And moreover, so it's a compact object. And if you close it up under shifts in both directions, extensions, and arbitrary co-products, so you iterate these operations, then you get the whole derived category. And that means that it's compactly generated by this module. Okay, yes, so this is also completely analogous to the case of ordinary algebras and to the case of DG algebras or DG categories. In the case of DG categories, you replace the free module by the representable modules. And then finally, we have an A infinity Morita theorem. If we take a compact generator, so an object which has the same nice properties as the free module, and we take B some A infinity algebra quasi-isomorphic to the derived endomorphism algebra. And here the derived endomorphism algebra is just the Hom complex as I defined it. Then we get an equivalence from the derived category of B to the derived category of A, which takes the free module, yes, the standard compact generator, to the given compact generator. Okay. Yes. So to make the link with the beginning of the very first lecture, maybe you remember at the very beginning of the very first lecture, I stated one motivating problem from representation theory. The problem was to tell the difference between a complex up to quasi-isomorphism and its homology viewed as a graded vector space. And I stated that this difference is precisely given by an A infinity module structure on the graded vector space. Yes, and if you combine the existence of minimal models with this equivalence, then you can prove that the solution I gave to this problem, the existence of the A infinity structure, is correct. Yes, so this gives the solution to that problem. And the second remark is that the theorem, so all these nice properties, extends to A infinity categories if we replace the free module with the representable modules, and we replace A infinity quasi-isomorphism with quasi-equivalence. Yes, then the same theorem holds. Okay. Now this, as I said, this derived category is an unbounded derived category. It's an enormous category. So it's useful because it contains nicer, smaller subcategories. And maybe the most basic one is the subcategory generated by the representables, the triangulated subcategory generated by the representables. We denote it by tria of A. And supposing that we have strict units, one can give a very nice A infinity category whose H0 is this category, triangulated subcategory generated by the representables. And this A infinity category, just notice that this is an essentially small category. And this A infinity category is the A infinity category of twisted objects. Okay. Yes, so let's look at an example. Suppose we have just an ordinary algebra concentrated in degree 0. Then the triangulated subcategory generated by the representables, well, there's only the free A module of rank 1. And this triangulated category is exactly the category of bounded complexes of finitely generated free modules up to homotopy. And well, when we have free modules, then we know how to describe complexes between them. Yes, the complexes are given by differentials. The differentials are morphisms between free modules, though they're given by matrices. Yes, so the objects are given by matrices, then clearly the morphisms are also given by matrices. Everything can be described in terms of matrices with coefficients in this algebra A. And now we would like to have an analogous construction in the general case, where we start with some A infinity category with strict units. So we would like to use matrices with coefficients in the morphism spaces to construct the A infinity category of twisted objects, which is somehow the most economical A infinity category, which models the triangulated subcategory generated by the representables. And by models, I mean that H0 of the category of twisted objects is this triangulated subcategory. Okay, so let me give you the definition. It is in 2 steps. In the first step, we close our category under suspensions and desuspensions. So formally, the objects are pairs consisting of an object and an integer. So think of this object as the nth suspension. Then morphisms are defined in accordance with this idea, simply by shifting the morphism spaces. And then the compositions are induced by the Mn of A. There is no problem here except the signs. Yes, the signs involved in this operation are quite subtle, but they can be computed. And then in the second step, we take the closure under extensions of this closure under suspensions and desuspensions. So now the objects are pairs consisting of a sequence of objects. So you should think of these as the subquotients of a filtered object. And then a kind of differential, namely, so this differential is a strictly upper triangulated matrix with coefficients of degree +1 in these morphism spaces, and and delta should satisfy the Maurer-Cartan equation. Yes, where we still denote by the same symbol. So these are now copies of the matrix delta, and we can of course extend the higher multiplications to matrices in an obvious way. And notice that it's strictly upper triangular. So as soon as the number of factors here exceeds the size of this matrix, this expression will vanish. So the sum is well defined. Okay, so these are the objects, and you third, since this is strictly upper triangular, it really corresponds to the situation where we have an object X, which is filtered with subquotients X1 up to XR. Okay, then morphisms are very easy. Yes, morphisms are just given by matrices with coefficients in the corresponding morphism spaces. Then the compositions are more interesting. Suppose we are given a sequence of twisted objects, and we are interested in the higher composition of a sequence of morphisms between these twisted objects. So how do we define that? Well, so we want to define this Mn applied to some chain of morphisms. Well, what do? We take this chain and we choose a position, and in this position, we insert a certain number of tensor factors equal to delta, to the delta corresponding to the object sitting here. Yes, and we do this at several places. We insert a tensor power of the corresponding delta. I guess that gives us something which looks like this. Okay, so this is a certain tensor, and we can apply the given higher operation with suitably increased number of arguments to this. And we do this in all possible ways and add in suitable signs, and that gives us the higher compositions. Okay, yes, so this is the construction, and then the theorem is that this is an A infinity category, and its H0 is the triangulated subcategory generated by the representables. Okay, so this is the end of this series of lectures, and as a dessert, another picture of the Stashev association. Okay, thank you very much.
I'm just trying to get it so I can see you. Has anyone got any questions for Bernhard?
Yeah, I asked a question in the chat.
Well, feel free to say it out loud.
Yes, so why is the category of A infinity modules only a DG category and not a general A infinity category? Yes, because you should view it as a functor category whose target is a DG category. So the target is the DG category of complexes of vector spaces. Yes, and because the target is a DG category, this module category, which you should view as a functor category, is just a DG category.
Why is the target category just complexes of vector spaces?
Yeah, if you like, you can view a module as a functor from the one object category to the DG category of vector spaces, graded, yeah, of complexes of vector spaces.
You mean then all the definition are equivalent?
Yes.
I see. Actually, there is a question before mine. It's also in the chat, I think.
The derived category of an A infinity algebra was constructed just by modding out homotopy. For the usual derived category of an associative algebra, this is not enough. That's correct. Could you elaborate on the distinct properties of homotopy and quasi-isomorphism in the A infinity case? Well, the big difference is that in the A infinity case, quasi-isomorphisms become invertible up to homotopy, yes, both for A infinity algebras and for A infinity models. Yes, so that's the big difference. Quasi-isomorphisms become invertible up to homotopy. Yes. There's something missing on the cloud. The notes stop after remarks. Okay, I will correct this as soon as possible. Yes.
And in answer to the other question, yes, we are recording the talks. They're made available online. I guess these ones will not be made available till Monday now, but they will be available. Are there any last questions for Bernhard?
Maybe one very simple question. What is a co-module over a co-algebra?
It's a map. Let's call M the co-module. Then it's the structure map is given by a linear map from M to M tensor C, where C is the co-algebra, and this map should be co-associative and co-unital if the co-algebra has a co-unit.
Could you maybe
it's the precise dual of the definition of a module?
Yeah, that makes sense. Could you maybe go back then to the definition of an A infinity module?
Yes. Maybe we should postpone.
Yeah, that's fine.
To next week, because I have to go to my thesis now, but I will turn up next week and answer any remaining questions, and I will also put the notes.
Yeah, okay, sorry.
Okay, well, then we should all thank Bernhard very much for his lecture series. Very much enjoyable. And yes, there'll be opportunity to speak to him next week. And for now, we'll take, I guess, almost a 15-minute break before the next talk. James, if you're here, you can get set up, but if you want to leave it for a bit as well, that's fine.
Okay, yes, I am here.